projects due today? I see a couple of them are already uploaded. Good.
Is it okay if we just upload it as a Word doc?
Yes. But it makes me sad.
How do you want it uploaded?
Sorry.
I mean, if you edit the Google site, that'd be fantastic. But if you really don't want to, that's okay.
Like embedded into the Google site?
Of course. That's why you have editing.
Oh, no, I was talking about just what we also have the ability to upload a document.
Yes.
That's
you
what I
have.
did.
Yeah, so, anyway.
Whatever you decide is fine,
Okay.
as long as it's uploaded and not emailed to me or something. Any other questions? Okay. Continuing vertical. Continuing vertical coordinates. So we saw last time that the choice of vertical coordinate mechanism, not just the choice of vertical coordinate, which you can choose from height coordinates, pressure coordinates, isotropic coordinates, or mass coordinates, makes a difference, but also the representation of topography involved. And that's basically how your coordinate scales as you go up, and your placement of corresponding model levels. So you have the capacity to choose a sigma coordinate if you so desire, in which case it'll scale linearly between a flat model top and with lower bottom topography. You can have a hybrid coordinate where it flattens out at some intermediate point, or you can have a even more complicated hybrid coordinate where not only does it smooth out at some intermediate point, but it also tends towards a smoother profile at an even lower level. So you basically hybridize it between various levels of smoothing and representation of the topography. By doing so, you have the capacity to do a better job of affecting stuff at constant horizontal velocity with no vertical exchange through those levels, and not having to deal with spurious exchange between vertical levels that you don't really want. So moving on then to the topic of vertical staggering. So analogous to the issues that we had in the horizontal with the A grid versus C grid, we also have this concept in the vertical direction. So treating the vertical as a one-dimensional simulation domain, we can stagger our variables in a variety of manners. Remember that we have 5 different prognostic quantities in the non-hydrostatic equations of motion, and we can take those and basically stagger them however we want. We can put certain variables on model interfaces, or we can put certain variables on model levels. Here the model levels are denoted by full integers, and the model interfaces are denoted by the half integers. So in the Lorentz grid staggering, you have velocities and pressure all located at the same point on model levels. So in terms of horizontal grids, what type of grid would that be equivalent to? In terms of the Arakawa grids.
Well, isn't it?
Oh, right. It's equivalent to the A grid, the Arakawa A grid. So you have velocity and pressure all located at the same point in space. And consequently, you would expect that you have the same issues associated with the A grid with this so-called Lorentz grid staggering. The Charney-Phillips grid, on the other hand, you have pressure and velocity staggered with respect to one another. That means that you can put pressure at model interfaces and velocities and other quantities at model levels. But as long as you have the pressure staggered in between, then this acts more so like an Arakawa C grid. So in order to see why this is the case, let's look at the Lorentz grid. If we look at the linearized vertical velocity equation, so in this case we're going to take the density field and assume some sort of background reference density, and assume that we only have a small perturbation from that background reference hydrostatic density field, as well as having a background pressure field, which represents a small perturbation from a background reference pressure field. We end up with an equation which is linear in the prognostic variables W, rho, and P. So in terms of how these quantities affect the vertical velocity, the presence of density purely affects the magnitude of a propagating wave. Namely, you would expect that if you have a giant SUV and you drive it into a smart car, that smart car is going to go a lot faster after the collision, correct? So analogous to that, if we have a wave which has very large magnitude at the bottom of the Earth, very small magnitude at the bottom of the atmosphere and it propagates upwards into a region of less density, we would expect that the wave would also grow in magnitude as it propagates upwards. So that's analogous to what this is representing right here. The pressure, on the other hand, affects the actual propagation of the wave, namely the wave speed or phase speed associated with the motion of the wave. And that's because it's coupled to a corresponding equation which basically looks like the change in pressure with respect to time is proportional to the z derivative of the velocity. So we're going to isolate just these two terms, the two terms that affect the propagation of the wave, and use that in order to show why the Lorentz grid has this computational mode associated with it. If we apply a semi-discretization on the Lorentz grid and just say that the pressure, the discretization of the pressure derivative at some velocity level, say k, is equal to the pressure at k plus 1 minus the pressure at k minus 1 divided by z at k plus 1 minus z at k minus 1. That'll give us an approximation for this derivative term right here. So this has the same issue that we discussed earlier with the A grid, namely we have the separation of the odd and even modes. Only these odd modes will affect even modes of the velocity field, and even modes of the pressure field will affect odd modes of the velocity field. So the two will basically decouple from one another. And consequently, the vertical velocity evolution equation is unable to see any sort of 2 delta x modes in the pressure field. If we have this sharp gradient in the pressure field here that looks like a V, the calculation of the pressure gradient at this point is simply going to look like a constant. So it's not going to be able to see that 2 delta z modes associated with the motion. Yes?
When you say odd or even mode, are you talking about, are you referring to the period? The number of grid points that make up a period?
No, I just mean odd and even levels. So, for instance, you end up with a separation where you have mode 1, where it's pressure at 1, 3, 5, 7, and W at 2, 4, 6, 8.
Okay.
And then you have mode 2, which is the opposite, which is pressure at 2, 4, 6, 8, and velocity at 1, 3, 5, 7, etc. So the point is that under the discretization that I showed you here, these two modes are completely separate from one another, because in order to evolve the velocity at point 3, let's say, it only depends on the pressure at point 2 and 4. So it never sees any of these pressure numbers up here.
Okay.
And analogously, in order to evolve the velocity at these points, they only ever see these pressure numbers in their corresponding modes. So you get this separation of the two, whereby these two modes never see each other in a discrete sense. And so consequently, they can evolve separately from one another. Make sense? So this is what's known as a computational mode. It's not particularly aptly named, but it represents the fact that there is this spurious behavior which is purely associated with the numerics and not at all associated with the physical nature of the system. In order to do the Arakawa-C grid representation, which is the so-called Charney-Phillips grid in the vertical direction, we have the velocity and pressure values staggered with respect to one another. So then the pressure appears at half interface levels, and the velocity is defined on model levels. So it's only affected by the pressure at the neighboring half interface levels. So in this case, you don't have a separation of modes, because for any choice of a pressure interface level, it will affect the two neighboring velocities, the two immediately neighboring velocities. So there's no capacity for a separation of these two separate groups of nodes which don't affect each other. So no separation of odd and even modes in the Charney-Phillips grid, and so it doesn't support this computational mode associated with motion. So there's been a lot of work in order to show that this is the case, and consequently a lot of modern atmospheric models will then adopt the Charney-Phillips grid in the vertical direction in order to represent variations of the prognostic variables of the vertical. This also means that you need to take into account the fact that your pressure is going to be offset compared to your other variables. So for there's other different staggerings you can choose. For the non-hydrostatic system, there's 5 prognostic variables. So we have the 3 velocities, u, v, w, and we also have a choice of 2 thermodynamic variables. There's a theorem in thermodynamics that basically says that you can write any thermodynamic variable as a function of any other 2 thermodynamic variables. So specifying 2 thermodynamic variables will specify all possible thermodynamic variables for you. This kind of makes sense in the context of the ideal gas law, for instance, where pressure is equal to rho times r times temperature. If you know rho and you know temperature, then you will immediately know pressure as well. So there's other variables that we can choose though, including, for instance, potential temperature. Are you guys familiar with potential temperature? So potential temperature is basically the temperature of an air parcel if it was brought down to a reference pressure level, adiabatic. But it's equivalent to it's a thermodynamic variable. It's a function purely of temperature and pressure, and consequently it fits into this framework. It's actually a very popular variable to use in atmospheric models to represent the thermodynamics rather than the temperature, because the temperature tends to misbehave, whereas data tends to actually be fairly well behaved. Some of these choices have computational modes, and we want to have accurate representation of waves in the vertical direction, including acoustic, inertia, gravity, Rossby waves. And these are best achieved by minimizing finite differences over distances of 2 delta c in the system. So this has been analyzed very thoroughly in this paper by Thuburn and Wollings. I don't think I assigned it as one of the reading papers, but it is a fun read if you're interested in this kind of stuff. Basically, for 3 coordinate systems, height base, pressure base, and isotropic coordinates, they considered every possible combination of distinct prognostic variables you could choose and their corresponding staggerings, and showed that for any choice of coordinate variable, there is only one choice of staggering that has 0 computational modes associated with it, known as the optimal staggering. So this is interesting because even doing something as simple as, instead of using pressure here, instead of using density on model interface levels, that'll cause the generation of a spurious computational mode associated with the system. Basically, some wave which this discretization is not able to see and is not representative of the dynamics of the system. Okay. Questions? Okay, so I'm going to talk briefly about semi-Lagrangian coordinates. So the notion here is we have already defined everything in an Eulerian context. Namely, we have a bunch of nodal variables or a bunch of elements where the prognostic quantities are defined as either averages or point-wise values associated with those points in space. We discussed briefly the Lagrangian context of things where you have fluid parcels floating around and you track the corresponding quantities associated with those fluid parcels. Semi-Lagrangian coordinates is kind of a hybrid of that. It says, okay, we're going to keep our Eulerian frame in the horizontal direction so we don't have to deal with huge deformations associated with these fluid parcels. But in the vertical direction, we're going to let the fluid parcels float. They're going to deform, they're going to become larger, they're going to become smaller. It doesn't matter. They're just going to float in space. The layer thickness then needs to be tracked associated with this motion, analogous to the volume of the fluid parcel. So if you have very strong updraft here, for instance, you need to keep track of the fact that that layer is moving upwards. So this is kind of analogous to that pseudo-density that was defined associated with the other coordinate variables. The advantage of keeping track of a layer thickness as opposed to keeping everything in an Eulerian context is the fact that if you have tracers now, so if you have some sulfur compounds or some pollutants or something like that that float into the system, they can't cross these floating interfaces because the interfaces are representing edges of fluid parcels. So as long as you're constrained within that fluid parcel, you will be constrained within the interfaces defined by these floating levels. So looking back then at the full equations of motion, the whole messy set of equations that we had associated with an arbitrary coordinate variable, if we have a floating coordinate, a floating vertical velocity obtained from a semi-Lagrangian treatment in the vertical direction, then there's no vertical advection through layer surfaces. So that means for the material derivative then, we can actually drop this term associated with advection, vertical advection. And in the continuity equation, we also have that there's not going to be any transport of mass through these vertical levels. So that simplifies the equations of motion pretty dramatically, in the sense that you can basically treat every interface level as a two-dimensional set of equations that you need to solve. So you only ever have to solve a bunch of two-dimensional levels, two-dimensional layers that don't have any interaction with one another. Okay. This is where you jump up and you're like, Paul, this doesn't make any sense. We know that things get transported vertically in the atmosphere, and what you're telling us now is that we can just use a coordinate transform in order to remove all that vertical transport in the atmosphere. Don't be absurd. And then you storm out. Clearly this happens all the time. Anyway. So the thing is, we need to have some sort of mechanism in order to deal with this massive deformation associated with the semi-Lagrangian system. Namely, if we have vertical advection here that is so strong that this layer just becomes thicker and thicker and thicker and thicker, we're going to lose all of our accuracy near the surface because suddenly we have one state variable representing a huge chunk of the atmosphere. So in particular, in the tropics, this is particularly problematic because you're liable to have large regions where you have very strong vertical updrafts associated with the system. So consequently, what we need to do is do a semi-Lagrangian treatment in the vertical direction. Namely, analogous to the semi-Lagrangian treatment that I talked about for the horizontal equations of motion, every couple minutes, like every 20 minutes, every 30 minutes of simulation time, we perform a remap. And we say, okay, we're going to take whatever has been deformed in the Lagrangian context and remap it back to an Eulerian context, back to a set of reference levels associated with the motion. And so that remapping procedure then is the analog of vertical transport between line levels. But the fact that you're doing it so much less regularly than you would in an Eulerian context means that you generally have a much more accurate representation of exchange between the levels. Because for what it's worth, tracer species which would normally be confined to a certain fluid parcel are confined in that domain for longer. So this generally occurs whenever the layer thicknesses become too thin or too thick. Then they're remapped to a fixed Eulerian grid. Okay? Questions? Yes.
Is that why it says 15 to 30 minutes and the remapping takes place, or is that because it automatically knows that it's becoming too thin or thick, and so it kind of depends on what the advection is at that time, or is it fixed the whole time? And
It depends on the implementation.
Okay.
In the community atmosphere model, which does implement floating Lagrangian coordinates in the finite volume dynamic core, recently in the spectral element dynamical core, it's on a fixed timescale, which also means that you have the tendency to blow things up before that timescale is met. Namely, if you have too strong of a vertical velocity and it causes layers to actually overlap each other, so a bottom layer will go above a higher layer, then you end up with problems. And that's been known to happen if you go down to sufficiently small horizontal scales. And in that case, you need to tune back your fixed remapping time to something smaller so that it doesn't cause problems. For some of the advection tests that we sometimes run with finite volume dynamical core, we have to actually remap every time step, which causes us to lose a lot of the advantages of having the semi-Lagrangian mechanism. One other advantage is the fact that the community atmosphere model is specifically tuned, that is, the physics is designed for semi-Lagrangian levels, which means that when the spectral element dynamical core came along with their own mechanism for treating the vertical and plugged it into the physics modules that are in the community atmosphere model, they weren't doing as good of a job anymore. But once they switched to semi-Lagrangian vertical, then they were doing a better job than the finite volume dynamical core, actually. So this is something you always have to keep in mind. It gets quite complicated. Any other questions? So I want to discuss briefly time step limitations, and this is a significant issue for any non-hydrostatic implementation of the equations of motion. Remember, in the hydrostatic case, the vertical velocity is diagnosed from the other quantities. So we compute it generally as a vertical integral of the horizontal divergence of the flow. In the non-hydrostatic case, W has the capacity to evolve, which also means that you support vertically propagating acoustic waves or sound waves in the system. And these are problematic from a time step standpoint because the maximum wave speed of the system happens to be the wave speed of those acoustic waves. So the CFL condition that we derived previously for numerical methods looks something like this. You have a wave speed times the time step divided by a grid spacing, and all of that whole ratio has to be less than or equal to 1. Okay? So in the atmosphere, the fastest waves are sound waves, which have a maximum speed of approximately the square root of gamma times the pressure divided by the density. Does anybody know roughly what this number is for the surface? Just without looking at your slides. Emily?
340, 343
Yep.
meters per second.
Roughly 342, 343. So that's 1.4 times 10 to the 5 Pascal divided by about 1.2 kilograms per meter cubed. And the square root of all of that is going to be about 342. And for the most part, this is pretty constant throughout the whole atmosphere. Even if you go up 20 kilometers, I think the maximum difference you'll see in the sound speed is maybe, it'll drop down to maybe 330 meters per second or something. So the big reveal, which you've seen already. I think when you print out the slides, though, you can't see the numbers that are hidden under these boxes, right? Ha. So consider this then. Pull out your calculators and say, if we have a sound speed of 342 meters per second, and we have a grid spacing of 110 kilometers in the horizontal direction, what's our time step constraint going to be?
A third.
Huh?
A third.
A third. Why is it a third?
Oh, never mind. Sorry.
There's a unit conversion.
Yeah.
Calculator. No, does nobody have calculators? Wow. Any guesses?
It's a third times 1,000.
Wow. Yeah. The math guys in the back of the room are showing you guys. Which is approximately 300-ish, 321 seconds. So that's the time step associated with horizontal grid spacing. This is the model time that we want to run at. This is about 5 minutes, approximately. Running at 5 minutes sounds good. We can do 5 minutes for a 100-year simulation. It takes a while, but we can do 5 minutes for a 100-year simulation. By the way, did you guys see that email that I sent out about discussing what would happen if we had a horizontal grid spacing of 1 meter? Yeah. Yeah. So, good luck if that's what he's trying. Anyway, so if our grid spacing is 100 meters, which is what it typically is in the vertical direction, then what's our time step constraint?
Third.
Yes. Approximately 0.3 seconds. We can't do this for 100 years. This is about 1,000 times less in terms of computing power, or 1,000 times more computing power needed in order to run our simulation at this time step. So in practice, the limiting time step size is going to be governed by the vertical coordinate. And here it's too severe. We need to deal with this. Can one of you name a mechanism that I might have talked about at some point that allows you to overcome time step limitations?
You have the implicit.
Yes.
Implicit scheme.
Yes, implicit schemes. You can do implicit in the vertical. You can do explicit in the horizontal. We have the technology. We can rebuild it. Are you guys too young to get that
Oh
reference?
my god.
Anyway, we can put a explicit in the horizontal and implicit in the vertical, and that'll allow us to overcome this time step restriction. And now we're running with the larger of the two time step restrictions. There are other mechanisms that we can use in order to do so, known as filtered equations. Since we know that it's the sound speed which is causing all the problems. So, quick quiz. If the sound speed was ignored, and the system was instead only dependent on the advection speed, what is the vertical advection speed in the atmosphere?
On average,
Yeah.
a centimeter per second.
Yeah, about a centimeter a second. Centimeter a second is much smaller than 300 meters per second. So consequently, if we can change our equations so that they don't support sound waves propagating in the vertical direction, then we can use that improved time step constraint. And hence our time step will be constrained by the advective wave speed instead of the sound speed. And consequently, we'll be able to pull off the 322nd time step size. There have been multiple attempts to do this, dating back all the way to 1962. Augur and Phillips proposed an anelastic approximation, which is probably the most well-known of the filtered equation sets. What they did was basically just dropped the time derivative term in the continuity equation. So they said that the density is pretty much static. It turns out that that also destroys a lot of the physical wave properties associated with the system, and so you want to do something better than that. Dale Durant from University of Washington had proposed the pseudo-incompressible approximation in 1989, and a unified approximation which brought together the anelastic and the pseudo-incompressible approximation was performed by Arakawa and Kohner in 2005. And Arakawa is still down at UCLA. He's in his 70s, mid-70s, and still comes into the office every day. It's very impressive. So the basic premise of this technique then is to derive a new set of equations which do not contain sound waves, and so the maximum wave speed is instead limited by advection. So these are both options for developing these atmospheric models, and both have been applied in practice. Questions? All right, so that's pretty much everything I wanted to talk about for vertical coordinates. So I will turn my attention to talking about global atmospheric models for around the world, moving away from some of the mathematics and moving more into a description of what other people have done, their motivations for making those decisions, and then after this we'll move into more discussions about parallel computing, some of the reasons why we would make decisions based on hardware systems, and then move into physical parameterizations after that. Keep in mind, I will not be here next Monday. I will be lecturing at Lawrence Berkeley that day. So enjoy. You should probably be working on your course projects. There we go. That sounds a bit more hard-ass. Is this being recorded?
Yeah.
Okay. So, why do we want to have multiple models? Pretty much, most of the developed countries have come up with their own modeling system, their own global atmospheric model. The US has something on the order of 6 or 7 of them. Britain has 3 or 4. Japan has 3 or 4, etc. I think even Canada has 2. I think Canada's winning in number of global atmospheric models per capita, actually. Here is a figure from NASA which shows the relative error metrics for a 20th century climate model intercomparison project 3 annual cycle climatology. So this is what went into the IPCC 4th report, I believe. Basically, it gives a measure of the relative skill associated with a bunch of important quantities for climate data. And the way that it's obtained is we run a simulation which has been initialized at a known point in time, say January 2005. We run it forward for a year and then compare their outputs against what we actually saw for the year. So here we have various quantities. We have, let's see, here. There's long wave radiation, you have zonal velocity, meridional velocity, surface temperature, velocity at 850 hectopascal, temperature at 850 hectopascal, long wave radiation outgoing, and short wave radiation outgoing. I'm not sure about all of the acronyms, but the point of this is, if you're red, that means you're doing worse than corresponding models. And if you're in the blue, then you're doing better than corresponding models. And if you're white, then you're just kind of in the middle. So we have all these different models laid out here on the bottom. So these are all from various organizations which participated in this CNEP3 model intercomparison, including models from the US, models from Norway, Canada, Japan. This is the Korean model, Britain, and the US CCSM, so that's the community climate system model. As we can see, every model basically has at least one part of this plot where they're doing worse than the model average. Some of them are doing much better than the model average for certain quantities, but especially something like the GISS model, so that's a NASA model, that's doing really horrible on a lot of these quantities. But if you take all of these models then, and then look at the model mean for each of these quantities, and look at the model median for each of these quantities, you obtain these first two columns here. So when you first look at this plot, you're probably like, wow, those first two models look really good. Why aren't we using those two? So this is actually the combination of all of these, the full set of models filtered down to a model mean and a model median. And in general, it seems to be the case that the model mean and the model median do better than any individual model. You can compute the skill scores associated with each of these models, and the mean will tend to do about 10% better than the best individual model. So the question is, why do you think this is the case? Yes?
I mean, could you say it's kind of like an ensemble of models? And so usually when you take when you average over say a year and you're doing a global mean, if you average that, usually it gives you a better result. It averages out all the perturbations and all the small scale stuff.
Yeah, that makes sense. Question for you.
Yeah.
If we were to run an ensemble of 50 simulations using CCSM,
Mm-hmm.
do you think that we would also do significantly better? No. Why?
The same model should have the same bias.
The same biases.
Yeah.
Yes.
Yeah.
So all these models are actually going to have individual biases associated with them. That is, they will consistently produce temperatures which are too low in one particular area, too high in another particular area. Maybe the precipitation is completely wrong somewhere, et cetera, et cetera. Every model basically has some sort of set of biases associated with it, which are constantly being worked on, constantly worked towards being fixed, but nonetheless, they still suffer from model biases. Yes?
I was wondering the errors, are they, because there's like 2 to 3 dimensions in space and a dimension of time, like how, like, is it calculated just like after the year, what is the time, or is it at certain places, or do they kind of try to make a norm over the whole like 4-dimensional space?
I think it's integrated over the whole year in the time dimension, and it's some sort of average over the spatial dimensions. For some of these quantities, all these numbered quantities down at the bottom, those represent specific vertical levels. So it's only a 3-dimensional integral in that case. But yeah, it's some sort of average. Presumably there's a spin-up period also associated with the model, so it ignores the first 2 months of the data, assuming that it's just the model getting into a quasi-balanced state. So, great.
What if you take out from the average all the like very bad models? What would happen?
It's a good question. Not sure. You have to have some sort of metric to define very bad models.
Well,
It's pretty clear that PCM and GISS AOM probably should be removed.
ensemble mean, and then you change how the rest of the individual models compare to that model mean, correct?
Yeah.
So technically, like these ones that are darker blue, if we take out the bad ones, may not be as blue
Right.
Yeah.
if we take out the,
Because they can be like in the extreme and they cancel out each other indirect.
Yeah,
Well,
possible. Well, I mean, if you're removing still models at the very end, then it's not going to really affect the shading on this too much. It'll make it slightly less blue, yes, as it drifts back towards, or as the mean gets better, presumably with those variables. But yeah. Sure. So kind of a world map showing our operational global atmospheric models. These include climate models and global numerical weather prediction models. So here on the left-hand side, we have the Naval Research Lab no-gaps model. That's developed down in Monterey. NPAS I put here at Los Alamos Lab, even though a lot of the work there is done at NCAR. NCAR has the CESM model, which includes 4 different atmospheric dynamical cores. The Environmental Protection Agency uses a model called the Ocean Land Atmosphere Model, which is developed out of the University of Miami. NASA is developed at NASA Goddard in Maryland. GFDL is in New Jersey. NOAA is in Boulder, Colorado, and NCAR is also in Boulder, Colorado. And so those are pretty much the gamut of US fully supported operational atmospheric models. Only 3 of those participated in the IPCC. You also have the Canadian model, the GEM model, Global Environmental Multi-Scale Model. Britain has a bunch, and it took me a while to squeeze all the text in for this. The UK Met Office Hadley Center model, they are renowned as having probably one of the better climate models. The Unified Model is also run at the UK Met Office. ECMWF is the European Center for Medium-Scale Weather Forecasting. They have a very powerful numerical weather prediction model. I'm not sure if it's ever been run in a climate context before, but their focus is purely on numerical weather prediction and producing good numerical weather prediction products. Meteo France has the CNRM model. Germany has 3. They have ECHM, ICON, and the DWD model. Norway, they have the Berknes Center Climate Model, BCCR. Russia has the INM model. Beijing, there's a model of BCC. Korea has the KMA model. Japan has a bunch of models with different focuses, including NICAM, JMA, and the CCSR MyROC model, which is one of the participants in the IPCC. And then Australia has 2 models, GEMS and CSIRO. So you have to be very careful in order to choose your acronym carefully. Many of them are taken. So I'm going to look briefly at some of the design decisions that have gone into a small set of these models. Sadly, a full page is a small set. So I'm going to go through these ones. Some of these were not mentioned even on the previous page because they're non-operational. So they're like university level codes. Inevitably there's this disconnect between atmospheric models which have been developed at a university level versus atmospheric models that have been developed at a national lab level. And typically that disconnect is that the university models have really, really nice mathematical properties associated with them. So they conserve certain quantities, or they don't have computational modes, they don't need extra diffusion associated with the system. But the issue with the university models is typically they also take about 10 times as much time to run compared to the national lab developed models, which focus more on operational products. So the one I want to talk about first is the Ocean Land Atmosphere Model. It was primarily authored by Bob Wacko from University of Miami, also with Ronnie Avasar and Martin Hunt. So this is an operational model. It's a non-hydrostatic model at deep atmosphere, so they don't make the shallow atmosphere approximation that I discussed, used by the US EPA in order to do global simulations of pollutant transport. So they went with an also support the dual to that. So if you actually take the triangles and put nodes in the middle of each of the triangles and connect those nodes to each of the adjacent nodes connected by going across edges, then you end up with a mesh which is composed of all hexagons and 12 pentagons. So you need to be careful around those pentagons if you're expecting it to look like a hexagon. They have the capability to do smooth mesh refinement in both a hexagonal context and in the triangular context in order to do regional modeling over that area. So this is known as conformal static mesh refinement over regional domain. The reason that it's conformal is the fact that every edge here is shared by exactly 2 elements. You don't have any weird situations where you have an element like this and then 2 elements connected on that side. This is what's known as non-conformal mesh refinement. In addition, they use a cut cell method in the vertical in order to improve the horizontal pressure gradient calculation. Cut cells are treated by scaling the surface area of the cells by the exposed area. So you compute fluxes across each of the cells, and then you say, okay, only about 50% of this edge is actually exposed. It actually would actually allow fluxes through that edge, so we're just going to multiply the total flux through that edge by 50%. And then that gives you a mechanism for incorporating cut cells into the calculation. All right, so those are the design decisions that they made. USIM is the next one I want to mention, the Unified Z-Grid icosahedral model. This one's developed by Dave Randall, he's in the readings actually, because he was one of the founders of the superparameterization method, and he did a lot with cloud parameterizations. He's probably one of the cornerstone figures in the field of cloud parameterizations. So he came up with, so this is a non-operational, non-hydrostatic, shallow atmosphere model based on a unified model system, and it uses a vorticity divergence Z-grid, which I haven't discussed so far. But the basic idea is basically change your equations around in order to get nice mathematical properties. So instead of storing a u and a v velocity at points within the grid, instead we're going to store a vorticity around the cell. So basically how fast the fluid is rotating at that point, and a divergence. So we want 2 velocity components, zonal and meridional. It turns out that this is equivalent. The nice thing is, instead of storing vectors, which can change depending on your coordinate system, here these are scalar quantities. So they don't change regardless of the coordinate system. And this is built on a hexagonal grid. So he actually wrote a famous paper in 1994 where he analyzed all these numerical methods and showed basically that the Z-grid formulation has the best numerical properties associated with it. But in order to actually obtain the velocity field at each time step, you need to do a global solve. So analogous to an implicit method, you need to do a global solve, which requires global communication. And consequently, the method is probably not scalable to large-scale parallel systems. So there's always this trade-off that you'll find in practice. The hardware people have certain demands, the software people have certain demands, and the scientists have certain demands. So if you're designing an atmospheric model, it's very difficult to appease all these groups simultaneously. So some of the features of USIM, third order multi-step scheme, Adams-Bashforth, time-stepping. I didn't even talk about multi-step time-stepping schemes. Tend to have some issues associated with them actually in practice. Positivity preserving flux corrected transport. So this is a mechanism for preventing negative tracer masses, which would emerge as numerical artifacts of the flow. He uses a unified approach for treating vertically propagating sound waves. So that's the one I mentioned, filtering the equations in order to remove sound waves from the system, but retaining Rossby and inertia gravity waves. And topography is not yet implemented, so it's really an experimental model. And he has many graduate students working on it. He has a ton of funding, so if you want to do a postdoc or something, you talk to him. Endgame, this is an operational model which supports both non-hydrostatic and hydrostatic and shallow and deep atmosphere. It always seems as though the British have the best atmospheric models, I must say. They get kudos for that. So this is developed by John Coburn, Thomas Melvin. So it's based out of Exeter and the UK Met Office. It's like a collaboration between the two. So the basic philosophy is a unified model, not to be confused with unified vertical coordinate treatment. A unified model used for both numerical weather prediction applications and climate applications. That means that the climate mode of the model must support the numerical weather prediction benchmarks. Namely, it needs to be able to do a 25-kilometer global forecast of 7 days in less than 3 hours of computing time. By holding it to this standard, it can also pump through climate simulations fairly rapidly. And there's a ton of very experienced people whose sole purpose is just to tweak the code in order to make it run faster on their supercomputing systems. But, interestingly enough, they run on a latitude-longitude grid. So, for all it's worth. In order to run on a latitude-longitude grid properly, first of all, you're not going to get large-scale parallel scalability. They have acknowledged that in the current system, they're not going to scale past 10,000 processors. For their numerical weather prediction applications, they're actually told you need to get this simulation done on this particular system. So all the tuning goes into designing for that particular system. And so once they take it and put it on another system, there's no guarantee that you're going to have the same computational productivity associated. So it uses a C-grid and horizontal, Charney-Phillips vertical staggering, so all the correct choices for the discretization. Fully implicit iterative scheme for non-advective terms. So it separates out the advective and non-advective terms and handles them separately. So it requires a global solve, and it requires some iterative procedure in order to basically deal with the fact that you have convergence of grid lines at the top here. And also the scheme is not inherently conservative, so this is basically a carryover from numerical weather prediction. They need to have a posteriori correction mechanism. So they say, okay, over this time step, we've lost 1,000 kilograms of mass from the atmosphere. Let's just put it back in. Okay, so that's probably enough for today. I will finish that up next time. And yeah, so see you guys next Wednesday. Are there any questions?